So hi, everyone. I'm Mohammed. I'm a PhD student in the Information Technology group, and I am delighted to be here today with all of you and my fellow presenters to share our work understanding how integrative experimentation can further our understanding of the role of punishment in sustaining peer cooperation. And so I'm going to start on a bit of a meta-scientific note, go into our approach and design, and then kind of take a look towards the future. But let's start with just a broad question. So throughout my PhD, groups have been kind of central to all the work I've done. I've studied how groups solve puzzles together, discuss contentious topics, and now I'm interested in kind of discussing how they cooperate with each other. And so, does punishment make people more cooperative? Spoiler, the answer is every social scientist's favorite phrase ever. It depends. And so, what does it depend on? Well, we can take the two terms punishment and cooperative, right? We can ask how strong is the punishment? So what kind of punishments are we talking about? But also the setting. So how incentivized are they to cooperate in the first place? These all vary between different topics, as do even the people, right? So how old are they? Where are they from? What do they believe? These factors can all affect the outcome that you might find from any given research study. And so in reality, every study lives in a space of people and experimental designs. And so if we were to answer this question of how punishment affects cooperation, we could come up with one experiment. So we're going to say we're going to run a public goods game with a given number of participants, a number of rounds, and we're going to have a control treatment, a control without punishment, and a treatment arm with punishment. And then we're going to recruit from the subspace of participants that live on prolific. And that's going to be our design. We run this study, we find a parameter, and we write the paper, and we say punishment is good for cooperation, right? The way papers are typically written does this. So it kind of makes claims about kind of the broad effect of punishment without clearly drawing boundaries of generalization. In reality, the paper might have kind of an area of validity around its design space. Right? And so you could run a different design with a different pool of participants. That same pool can have a different experimental design. And really, you start to see that every paper lives in this kind of space of research design. And the question is, how do we go from beta punishment based on a single experiment to learning the underlying mapping from context to effect, right? And if you look at kind of how we typically design research, right? You write a grant, you get a lot of funding. You say, I'm going to run a high-powered experiment because I want to precisely estimate the effect of punishment. But what if instead of this big experiment, we ran hundreds of micro experiments? So individually, these experiments are not informative about that specific combination of factors. But when we run these different micro experiments and we integrate the results, together they can facilitate macro understanding. So we can understand how the phenomenon of interest changes across the design space. So this is the dream, or rather the pitch, right? Now, how do we put it into practice to understand the role of punishment in sustaining cooperation? So to do this, we study the setting of public goods games. And so this is a stylized game that kind of reflects a lot of real-world scenarios we might run into. For example, taxing to provision public services. And to kind of get us all on the same page, in a public goods game, you have a set of players. You give each of them an endowment, so $20, and you ask them you give them the option to contribute all, some, or none of it to a public fund. The total amount that's contributed to the public fund is multiplied by a given factor to generate a shared benefit, which is divided equally among all players, regardless of their initial contribution. So to highlight the fundamental tension here, if you look at the blue player, they contributed nothing, but they made out like a bandit because they withheld their initial endowment and got a slice of the shared benefit. Whereas if they had contributed their full endowment, the total amount of money in this microeconomy, which we call social welfare, would have been higher. And so in these settings, punishment has been widely studied as a mechanism to sustain cooperation, where some branches of research have found that punishment, or argued that punishment is net positive. So even if you never implement it, the threat of it is enough to sustain cooperation. In some cases, people have argued that it's a net negative. So the cost of implementing punishment, so we ask people to pay an amount to deduct an amount from someone else. The cost of getting that additional benefit outweighed the benefit. And the third brand of research says, well, maybe if the game goes on long enough, you can reap the rewards of kind of whipping people into line, right? And so we're interested in this dependency. We want to really take it to the extreme and understand what's going on here. And so to do so, we combed the past 25 years of literature on public good game, and we defined a 19-dimensional space of design. And so if we were to categorize these different design factors, there are game design factors such as how many players there are and how long the game goes on for, but there are also things related to how strong the monetary stakes are, as well as the strength of the peer incentives. So people can punish each other, and that has cost and impact, but they also may be able to reward each other. And then we also manipulate information display. So how much they know about the game and about their fellow participants. And what's important to note here is I showed you a long list of papers in the past slide, but in each of those papers individually looks at one combination of these parameters, right? In this study, we're simultaneously manipulating all these factors together. All right, so to do so, we have a design space. We need a way to explore it. And to do so, we built an apparatus that, given any combination of these parameters, can generate a browser-based public goods game matching that configuration. And so this is one example screenshot from our game where you see this is the first stage of the game where people are deciding how much to contribute to the public good. Anything you see in blue, such as the availability of a chat window, whether contribution is by default or opt-in, et cetera. Anything in blue is parameterized. And this is true for every view of our game. So the game is entirely dependent on that set of parameters. So we have a space. We have a way to explore it. What are we going to do next? So if we look at the set of literature from the past couple of decades, and we map it to our dimensions and then project that onto a two-dimensional space, we can kind of start to illustrate what our design is doing differently. And so if we take a sample of these papers that have been published, you kind of see where they live in this projection. And they're not showing up on here. OK, there we go. So we run two waves of experiments. The first wave of experiments is kind of a high breadth, low precision. So across all these hundreds of points, each orange point is a combination of public goods games factors, and we run one game with punishment and one without. And the goal of this learning wave of experimentation is to train models that will predict the effect of punishment in unseen experiments. These unseen experiments are drawn from are randomly drawn from the design space. And so whereas the learning wave was a space-filling sample for high breadth, we just randomly pick 20 conditions, and we run a low-breadth, higher precision wave of experimentation. So the idea here is we're going to use this second wave of experiments to evaluate the predictions made by models trained on the learning wave. And we want to precisely measure our ground truth, which is why we run this higher precision set of experiments. So what have we learned from this data that we collected, right? If you look at the average effect of punishment, it seems to increase cooperation in terms of the coins contributed to the public good. And so that's only half the story. If we look at the net effect on efficiency, which is a measure of how the behavior of a group approximates that of a fully cooperative group, we see that maybe those guys who said, you know what, punishment is not worth it after all, maybe they might have had a point. And so the average effect in both waves seems to be that punishment decreases normalized efficiency. But this is obscuring important heterogeneity. So if we look at each of our 20 pre-registered validation wave experiments, we see that the effect can range from negative to positive, and with values in between. And so the question is, if there is important heterogeneity, can we learn to predict it? Can we find that mapping from the design space to the effect of punishment? And so we framed this prediction task by asking, given the design of the game, and the outcome in the control arm predict the outcome in terms of cooperation in the treatment arm. So you can think of this as kind of a decision maker knowing the status quo and deciding whether to implement punishment or not. And our models do fairly well with a range of performances. Our best performing model is an elastic net with two-way interactions. And you might look at this and say, well, how do I understand whether this is practically useful or an important level of performance or not? So we can contextualize this by looking at similar efforts in literature. For example, predicting whether teams will exhibit synergy on unseen tasks, or predicting life course outcomes such as dropping out of school, GPA upon graduation, et cetera. We seem to be in the range of predictive performance for those tasks as well. But an interesting benchmark here is also asking how well experts, so academics in the field, and lay people can predict these outcomes. So we give them the same prediction task using this interface, and we find that our models outperform both the statistical baselines of, for example, taking the average treatment effect from the learning wave and these predictors. So on the x-axis, we're looking at the true efficiency. On the y-axis, we're looking at the predicted. The ENET and OLS here are our two best performing models. We see that they outperform the expert wisdom of crowds and layperson wisdom of crowds, which is just the average prediction within each group, as well as the mean from the learning set. So if you take the mean under treatment from the learning set, the statistical models are outperforming this baseline. And you might say, well, what if this is just a function of the 20 validation experiments that you sampled? And for that, we bootstrap the predictive performance, which is the error bars that you're seeing here. And we find that ElasticNet and OLS seem to consistently outperform the static baseline. And so the question is, well, how do we loop this back into theory? And so to do so, we can ask which factors are influencing the effect of punishment and cooperation the most. And here, you kind of really need a complementary approach of two measures. So on one hand, we look at permutation feature importance, which tells us how important each factor is to our ability to predict the effect out of sample. And then the complementary measure is the tried and tested SHAP values, which show you kind of the magnitude of the effect of the factor on predicted efficiency. So think of it as how important is this factor to effectively predicting out of sample, and then what is the effect of this factor on the predicted efficiency. And so some factors like communication, so whether we allow people to chat, have very important roles to play in predicting efficiency and unambiguous effects. So it's clearly helping and when it's available and harming when it's not. Some factors like game length have more ambiguous effects. And so this is where the integrative experimentation approach can really support theory in ways that were not possible otherwise. So for example, if we look at the effect of game length on efficiency, we see that it's modulated by the availability of peer outcomes, so whether people know how well other people did. But then there's this third kind of level of the interaction, which is the availability of peer communication that can flip this effect entirely. So while our experiment doesn't identify exactly the mechanism by which this is happening, it identifies this interaction in a way that inspires future research to target these mechanisms directly. That would not be possible under other designs. And so cumulativeness is the primary objective of this type of design. We're releasing both the data and the apparatus that we use to generate this data. And the goal is that kind of it doesn't stop with this work. Other people can take our apparatus, say, you know, I don't like the region that you explored. I'm going to run everything else. But because they're keeping the interface consistent and the operationalizations of these different factors consistent, the research can then integrate and reinforce each other. And it's also a generative agenda. So this data set has been used to ask other questions, such as whether LLMs or other interactive agents can change group cooperative norms if we just inject them into this group, but also how we can use this data to influence cooperative behavior exhibited by LLMs. So for example, there's research by Binns et al. That looks at discrete choice experiments and fine-tunes LLMs on that data. our data is unique in that we also have conversations. So people are conveying threats, and they're establishing norms via text. And this presents an exciting opportunity to kind of augment that existing line of research. And so how can you adapt this approach to your domain? It's really 3 key steps. Define your design space, explore it systematically, and then evaluate your ability to predict. And with that, I'm happy to hand it over to the judges for questions.